NASA's Space Launch System stands perfectly motionless on the pad, holding millions of pounds of metal and fuel in absolute stillness against the sky. Sir Isaac Newton laid out the rules of motion centuries ago, and the first one states that an object at rest stays exactly where it is unless an outside force makes it move. Right now, this rocket is trapped by balanced forces. Gravity is pulling its massive weight down toward the center of the Earth, while the concrete launch pad pushes back up with the exact same amount of force. The result is zero net movement. To break this stalemate and lift off, the rocket has to generate a massive, unbalanced upward force, a push that violently overwhelms the vehicle's own weight. But you can't build a vehicle like a car or an airplane for this job. Wheels need a road to push against, and jet engines rely on spinning blades to pull in atmospheric air. Those methods are useless when the destination is the vacuum of space. Escaping Earth requires a self-contained propulsion system that relies on the raw, brute force application of physics to get off the ground. That brings us to Newton's third law of motion. For every action, there is an equal and opposite reaction. You've likely felt this yourself. If you turn on a garden hose and water squirts out the front, you can feel the nozzle push backward against your hand. This diagram shows how an engine uses this principle. Inside the chamber, propellants burn and expand. Ejecting this hot gas out the back serves as the action. Expelling it downward triggers an equal reaction force upward, physically pushing the massive vehicle towards the sky. This action-reaction rule even solves the problem of steering mid-flight. By slightly tilting or gimbaling the engine nozzles to redirect the exhaust stream, the reaction force pushes the vehicle in the opposite direction. Lifting millions of pounds and guiding it through the atmosphere both rely entirely on throwing a huge amount of mass in the exact opposite direction you want to go. How exactly do you generate enough thrust to lift a skyscraper-sized machine off the ground? We find the answer in Newton's second law: force equals mass times acceleration. To maximize the upward pushing force, the rocket needs to take a large mass of propellant and accelerate it out the back of the engine as fast as physically possible. This cross-section reveals the geometry required for extreme speed. Combustion products enter a wide chamber and are squeezed through a narrow central throat. Like placing your thumb over a hose, this forces a slow flow into a high-speed, high-pressure stream, accelerating particles violently outward. As the engine aggressively burns through thousands of gallons of heavy liquid fuel every second, the physical vehicle is constantly losing weight. Because the rocket's overall mass is rapidly dropping while engine thrust remains steady, the vehicle's acceleration increases the higher it climbs. A rocket achieves orbit by aggressively shedding its own weight. This reduction in mass allows the vehicle to accelerate faster, even while engine thrust remains constant. Eventually, the rocket breaches the atmosphere, hits orbital velocity, and the engine shut down. Out here in the vacuum of space, atmospheric drag, the friction force that slows moving objects down on Earth, disappears. We can now revisit Newton's first law, specifically the second condition. An object in motion will remain in motion in a straight line, unless acted upon by an outside force. Without air friction or a strong gravitational pull to slow it down, the spacecraft enters a state of endless coasting, riding on its accumulated momentum. NASA probes launched in the 1970s, like Pioneer and Voyager, are utilizing this principle right now, traveling deep into interstellar space without consuming a single drop of fuel. Rocket science succeeds by exploiting the laws of physics rather than fighting them, turning the bonds of Earth's gravity into a path for exploration.